Good morning, good afternoon, and good evening, everyone from all around the globe. My name is Eric Mayo, and I'll be helping moderate today's webinar, Parallel Computing for Enterprises in Julia. In this webinar, the discovery topics will be SIMD, single instruction multiple data, multi-threading, multi-process architecture, and GPU programming. We'll also briefly review the need for parallelism and some of the successes we've experienced with Julia's parallel capabilities. We'd like to have an interactive session today. Professor Edelman loves interactive questions, so please unmute your line and ask away. We're happy to hear dogs barking, lawnmowers buzzing, infants crying in the background, no worries. Otherwise, please write your questions in the chat and we'll either address them on the fly or address each question individually following the demonstration. With that said, I'd like to introduce you to today's presenter, Professor Alan Edelman, Professor of Computer Science and Applied Mathematics at the Massachusetts Institute of Technology, Director of the Julia Lab at MIT, co-creator of the Julia language, and co-founder and chief scientist at Julia Computing. Please welcome Professor Alan Edelman.
Hi, everybody, and I'm quite serious. I'd like to invite you all to turn on your video if you're not feeling too shy. I don't mind if you're munching on your lunch at the same time. So by all means, turn on your video if you feel comfortable to do so. I'd rather look at faces than just my screen. And generally speaking, it's okay to interrupt with questions. Probably the best way to do it is remain muted until you have a question, but by all means, just to avoid distractions, but by all means, ask away anytime. My students at MIT do that all the time, and I'm pretty used to it, and I prefer that. So feel free to say anything at any time that comes to your mind. So thanks, Eric, for that nice introduction. So just a brief word about myself. I'm Alan Edelman. As Eric described, I sort of wear a couple of hats. I'm a professor at MIT, and I'm the chief scientist at Julia Computing. And for some of what I'll be doing today, I'll be giving a bit more of sort of the professor's vision of where we are and where we're going. So I hope that'll be of interest to you. Before I do that, though, let me kind of start by doing something very concrete, which if you'd like, you can do it as well. I'm going to go over to Julia Hub, which is Julia Computing's basically window onto computing with Julia, which you can do directly yourself. So let me just do it. I'm going to go to Julia Hub just by typing Julia Hub, and here I am. And if you'd like to do this in the same time, you're welcome to, but I'll mention that because we're going to be using some cloud computing, it will ask you to put in a credit card. If you're comfortable to do that, that's fine. If you're not comfortable to do that, that's okay too. You will get $25 of free credits from the start. So for what we'll do today, it should be free of charge. But I guess we can't let, we're using third-party computers. And so if we need to let them run. So here, let me go ahead and I'm going to log in. There are a lot of ways to log in, but I'm going to log in with Google. I've got my whole family here, Google accounts, but I'll pick mine. All right, so I've already set up with a login. My credit card's already in. So what I'm going to do is just to get things going, and I'll say what some of the things mean. You could work in sort of a notebook mode, and I'll say a few more words about that. But this is Julia's notebook world, or you could do in sort of a more traditional editor mode. And so this is the VS Code approach. So what I'm going to do is I'm going to click this one. And because we're doing parallel computing today, I'll pick a GPU, and I think 4 processors. Well, maybe I'll switch to 8 processors. And we'll do it on the V100. That's a cool GPU. And I'll limit the time to 2 hours so that even if I forget to stop this at the end, which the clock keeps ticking, and if I stop it, the clock stops. I'll only be charged $9 for 2 hours at the most, and so that's not too unreasonable. So I'm going to start this going, and I will mention that at the moment, the time it takes to spin up a instance with a GPU can be as much as 10 or 15 minutes. And so that's the downside. But once you get your instance, it really works very, very well. So in about 10 or 15 minutes, this connect will be a darker blue and I'll be able to connect. And I could have started this 10 or 15 minutes ago. I was this close to doing it. I almost got on the machine and said I'm going to do it so people don't have to wait. But then I decided that's no fun. I want you to see the thing going in live action. In fact, I always do live demos. It's sometimes scary, but I always try to do some live demos. It's much more fun to and more believable to see things really, really working. So so that's Julia Hub, and if you want to come in and do it with me, that's fine. Now let me just give some background. I know that this is going to come up in about 10 or 15 minutes, and so I'm going to get back to that. And I thought I would start a little bit with a talk I gave over at Supercomputing, because it really conveys my feeling, my philosophy quite well. And so what I'm going to do is take this PowerPoint and go into slideshow mode. And hopefully you can all see this in slideshow mode. Is that correct? You don't get the weird notes mode, do you? Eric, does that look okay? Do you see
That's
the
great.
power language? That's good. Okay,
Yep.
great. Okay, so these are some slides that I gave a talk in the big supercomputing conference, where parallel computing sort of like a big deal. This was over in Denver. This was the last one before things went virtual, and this was a prize-winning talk. This was the Cindy Fernbach talk, and uh, I was giving a talk that at the time I think was considered surprising, perhaps not anymore. Uh, but I wanted to talk about how language makes a difference, right? The real power of language. And so the way I kind of framed this talk, and I'd like to share it with you, is to talk about the power of language to be productive. Also, the power of language to be impactful, right? The power of language to get abstractions, the power of language to build community, which people don't appreciate as much. But whether that's community within your own organization or around the world, the power of software language to build community is not to be underestimated. Okay, the power of language to be able to reuse code so you don't have to reinvent the wheel is another one. And for me, with my professor's hat on, the power of language to engage students so that we can get high performance computing, whether various kinds of parallelism at. So this was a lot of fun, and it's kind of a little bit dated, but I think you'll enjoy it anyway. So let me tell you about this supercomputing conference, and I hope I can set the scene. So I'd like to place you in the position that the audience was in. So if you're not familiar with these supercomputing conferences, I can tell you that they're given every year, and it's always the week before Thanksgiving. So it's always in November, and it's the week before Thanksgiving. So knowing that everybody was kind of in the Thanksgiving is coming mood, it was going to be next week, I decided to pull a graphic of a second grade social studies kind of exercise that maybe you did yourself when you were little, or maybe you have children who have done this, or but to compare Thanksgiving past and present. And in the past you have what clothing used to look like, and transportation, and so forth. And in the present, what clothing looks like, what games children play, and so forth. And following on that fun little Thanksgiving second grade social studies theme, I decided to talk about the week before Thanksgiving, past and present. And I wanted to give a kind of comparison of supercomputing as it existed, in 30 years ago, and as it exists today. So uh, so just to give a perspective of where we've been and where we are, and ultimately where we're going, of course, is the most important. So back in 1990, there were these machines called the connection machine and the Cray. And to this day, I think that this is the best looking computer that has ever been built. So if there's ever been a supercomputing beauty contest, I would say that the CM2 over there, the Hypercube, was the winner. Uh, but that's my opinion. I guess beauty's in the eye of the beholder, but I think this is a gorgeous machine. Uh, these days, the most powerful computers are in US national labs and in other similar places around the world. And they're very, very complicated machines, but they can do millions of times what my computer can do today. So back in those days, everybody kept talking about performance, performance, performance. Can you get a gigaflop? Can you get a teraflop? Can you get a petaflop? Can you get an exaflop? Right? These are the questions. These are measures of performance. With increasing powers of 10. Uh, Nowadays, people are more interested in impact, and impact could be measured if it's open source course code. People are interested in many users, and of course, if it's enterprise code, if it's for businesses, people want to know, is this really going to do the job? Okay, so in the old days, people cared about users would just write a paper about what they saw. Nowadays, at least if it's open source, people want reproducible science. And again, in the enterprise, people want guarantees that this will work. Okay. In the old days, people didn't care about composability, which means that one computer program works nicely, plays nicely with another computer program. It was enough to get one program working for people to be excited. Now, because the software chains are so complicated, everybody needs composability, and that's not so easy to do with high performance computing. Uh, in the old days, people talked about portability a little bit. Nowadays, it's a must, because everybody knows that the machine that you tune for today will be gone next week, right? I mean, I'm exaggerating by next week, but I think we all agree that computers come and go quickly. And so if you write codes that are very fast on one machine, and it's not going to be valuable on the next machine, it has very limited utility. Okay. Uh, in the old days, there was this thing called PVM, which I guess is hardly used anymore. Nowadays, one of the old standards of MPI is definitely showing signs of age. Uh, Back in those days, it was a smaller, younger community, but nowadays the young folks have many choices of what they can do with themselves. In the old days, there were sort of limited industrial connections, but now it's easy to imagine many more industrial connections. Okay, and uh, and really, in the old days, the workflow for success was basically roll up your sleeves and spend a lot of time performance engineering. And that's just not acceptable anymore. People don't have the time to do this. We need more automatic tools. And the nature of the tools that exist these days kind of go from here to here with increasing abstraction, increasing difficulty, but increasing ease of use. And so, that you can get performance out of libraries, you can get performance out of SDKs, or out of domain-specific languages, DSLs. But the approach that we're taking with Julia, both in the academic world and at Julia Computing, is to use high-level languages. We believe that with high-level languages, we can get performance out of parallel computers and still keep the code portable for many years to come. All right, so that's the big picture of what I've seen over the last 30 years or so, 3 decades of, this must be my first, this was probably my first supercomputing back in 1990, and this would have been the most recent one that I attended live back in 2019. So, but you see that the evolution, basically, if I have to sum this up, it would be this, that it has to be easier to use, and still performance is a must. But quick performance is what people really want. Okay, so, okay. Let's see, there is, okay, yeah, and I see Eric's request in the chat, so I'm going to echo that. Yeah, by all means, feel free to ask questions anytime you like. Okay. All right, and for some reason, my thing is not scrolling. That's weird. Oh, my whole computer is. Can people hear me?
Yeah, I can still hear you. Sometimes Zoom likes to take control. Maybe if you like Alt Tab, things will come back to normal for you.
Yeah, it's completely over my PowerPoint. It won't let me advance or.
There you
go. Now it'll go. Huh? I don't. Oh, I think I know what happened. I see what happened. Okay, I moved my Zoom controls out of the way, and it gave me the strength again. All right, one kind of fun slide of philosophy, if you will. Again, with my professor's hat on, that there's a lot of historical precedent among philosophers and mathematicians of how language matters, and so to kind of take a few favorite quotes from famous important people, and also a graduate student working with me. I kind of embarrassed him. This is Valentin, my graduate student. But you know, it's worthwhile spending a few moments thinking about language. Bertrand Russell, for example, said that it not only serves to express thought, but to make possible thoughts which could not exist without it, right? And Poincaré, who's a famous mathematician, basically said that when language has been well chosen, one is astonished with what you can accomplish. Okay, and the philosopher Wittgenstein, said it's kind of the other way, the converse, that the limits of my language are the limits of my world. And then there's my student Valentin, who again I've embarrassed, but he likes to talk about that computer science language is like applied psychology, and that we can coax performance out of people without them even really knowing it. Okay, let me skip past this, but people tried to do it 15 years ago. You might ask what's new with Julia, in case you were around back in those days. But basically, what was missed 15 years ago is basically what we have today is a multidisciplinary unit interface for high productivity and high performance. So another word, I'll say more about this stuff in a minute, but here, let me go back to this slide because this is also fun. When I was at this conference over in Denver, I at the very front of the exhibition hall is if you're ever in Denver, the big conference center has this big blue bear out on the front. I remember at the hotel they told me to just keep walking until you see a blue bear, and I didn't even know what they were talking about until I saw it with my own eyes. But inside the center, the high performance computing people kind of set up these banners with HPC throughout the ages, right? So every year they talked about what was new in supercomputing that year. And so I kind of took a picture of that with my phone, going back all the way to 1990. And what I noticed was that back to, actually it was the first one, I guess, was 88. Back in 1988, all the way up to 2010, as you could see on this timeline, there was some mention of programming language on each and every one of these banners, except for one, 2005, for whatever reason. But there was one every single year. And then the next decade, I call this the dark decade, because there was no mention whatsoever of programming languages everywhere in between 2010 and that year's conference. So something definitely seems to have gone wrong. And we in the Julia world are getting, we're breaking through the dark ages and fixing that. All right, so let me see if I can go back now to my to my spin up here and see if, yes, I can now connect. Okay, and so let me go ahead and do that. So I haven't even checked. I probably would have been able to do this maybe 5 or 10 minutes ago, but anyway, I can now connect to the Julia IDE. And so let me go ahead and just do that. Let me press the connect button and you'll see what happens. Okay, so I've got this nice welcome screen. I can make it bigger so that it's easy to see for the audience over here. And there's lots you can do here. So some of you may recognize that this is a VS Code window. It's basically a pretty popular editor or environment for writing code these days. You don't have to do VS Code. I myself just started using VS Code about a month ago and found it just quite easy to use. And I started to understand why other people really like it so much. But here's the VS Code welcome screen. You can also click on this other tab and you can play around and click. It's pretty easy interface, all in all. You can get to documentation over here. There are a lot of things. What I'm going to do, though, I think I want to go ahead and actually show you a real example of parallel computing in practice. And so I have this example that I shared back in the supercomputing world. And so I'm just going to show you this example first. Here I have it in a Jupyter notebook, which I'm not going to use, but it has some nice pretty pictures. And then I have the same code over in a VS Code. So what I'd like to do is tell you about my true dream for high performance computing and point out that this is not a dream anymore. It's an actual reality, right? So we can actually do this sort of thing. So in this dream, I'm going to take an example. I'm a math professor, so you'll have to forgive me. I'm going to take an example from linear algebra. Now, let me point out that there's nothing special about my example about linear algebra. If you're like me and you like linear algebra, that's great. You know, as a math professor, I'm always happy when people say they like math of all kinds. If you don't like linear algebra, you never took a math course, you don't even know what linear algebra is, it doesn't matter, because the point I want to make has nothing to do with linear algebra. The point I want to make is you can write code on a serial computer, and if you're lucky, if you do things right, this very same code could work. It could work on multiple CPUs, or it could even work on a GPU, right? Um, so you might have more than one CPU, or you can actually have a graphical processor unit which runs very, very fast. Okay, and I want to show you how you can do that, but I'm going to do this with a linear algebra example. So I hope some of you like linear algebra at least. And again, if you don't even know what linear algebra is, it doesn't matter. But what I like to do is talk about the fact that um, that a lot of times in this world, uh, there are libraries or software packages that will do a job for you, okay? But then there are other times when the libraries and the packages are not available for you because you're doing something special. Now, maybe you're over at a company and you have a unique product, a unique offering that you're building that nobody else is making public, right? You want to keep this to yourselves, or you're doing something new, that you're innovating, you're going past what everybody has done before, right? So what what might happen if you're going past what the library offerings have? So here, what I'm going to do is I'm going to show an example from linear algebra um, where I have a matrix. A matrix is just an array of numbers. I have a matrix that neither fits traditional categories like dense and sparse. So in the world of linear algebra, a dense matrix is an array of numbers that where there's mostly non-zeros. And a sparse matrix is one where there are a lot of zeros and software can take advantage of that. So whether you're familiar with linear algebra or not, you probably know that multiplying by zero is a waste of a computer because that's easy. You could do that one in your head. And adding by zero is also easy, right? You could do that in your head. And so if you have large arrays and you're processing them, but you're multiplying by zero or adding by zero, you don't want to waste precious computer time doing that because it's an unnecessary operation. Okay, but what happens if you have instead a matrix that's structured? And so I'm going to give an example of a diagonal matrix. Here's a picture of a 3x3 case. I have a diagonal matrix. So the three parameters are V1 and V2 and V3. And to that matrix, I add an outer product, which is just a multiplication table, right? You'll see this is V1 times V1, and this is V1 times V3. So I'm going to add this. And for whatever reason, this is a matrix that's not in the libraries. Okay, it's just none of the famous libraries will work with this matrix. So what I'm going to do is I'm going to build a custom type. This is learning a little Julia now, a little fancy Julia, I guess. By the way, if people want to tell me that they've never seen Julia before, I can actually show a little bit of basic Julia first. Oh, you know what? Let me sort of interrupt myself for a second because I don't know what your Julia familiarity is. But let me tell you one fun way if you'd like to start learning Julia. Yeah, this is like a commercial interruption. May I do this? You know, we now have an interruption from our sponsor. What I'd like to do is tell you about the class we were just teaching at MIT. So so here let me go to the front page here. So anybody here can go to it if you want. It's computationalthinking.mit.edu. The semester just ended, which, by the way, whether you're a student or a professor, the last day of classes is always a happy day. That was yesterday. So you can go here. Let's put it in the chat just for fun, if I can find the chat. So here it is. So I'll place this here, computational, if I don't type it wrong, I should have copied and pasted, but there it is. Computationalthinking.mit.edu. This is the class we just taught. And we decided to make a course that that was a combination where you actually learn Julia at the same time as learning some computer science and learning some math and learning some applications, kind of in an integrated way. And I'll tell you, I have trouble even explaining to my colleagues what this is. And so I tell them to just go ahead and play with, go in and take a look at this. For example, some of these things actually execute right on the web. Otherwise, you could download these things yourself. But if you want to play, just to show you a few fun things we did, here's a webcam which actually sees me live. Right, this is exactly live. And you can press on this, and you'll get a little mosaic. Whatever you do. So students love this. They can play around and they could start to see how Julia arrays work at the same time as having a little bit of fun. So, here, this is my corgi Philip, who I'm surprised is not barking yet, but you might be treated to his barks before the hour is up. And you could see him, you could just see playing, a lot of interactivity, which everybody likes. The students like it. So we put a lot of interactivity into all of these. And we really wanted, we actually had a hypothesis that unlike traditional work where you might learn the math on a blackboard and maybe you would program it up, or the science on a blackboard, and then later you would program it up afterwards, we thought it would be more fun and maybe even more pedagogical if you could actually have the programs first to play with, and the math would sort of be, you kind of learn it by osmosis rather than having to take it all in at first. And so we had these 3 modules. One was image processing in various ways, and you can see there's we did a lot of fun things, and I'd encourage you to look at this. We could, well, there was this, which was the one, was this the one? There was one where we put, maybe it was this one, where we combined, we combined the corgi upside down. These my dog's a corgi. Yeah, upside down and right side up. And I guess everybody in the class knew about this effect but me. But there's this tendency where if you took half of a right side up image, do you guys know this one? Half of a right side up image and half of a upside down image, and you blend them, so there they are. Your brain actually will always see the right side up. It'll somehow dominate in your brain. Your brain doesn't want upside down dogs or faces. Okay, and this actually is known as the face inversion effect. This is what the students taught me in the Thatcher effect. But it actually works on dogs as well, not just human faces. Anyway, I just wanted to share with you. And then we ended up with a whole module on climate modeling, and we kind of taught differential equations at the same time. And the students thought it was way more fun than the differential equation courses they took. And so if you never even took a course, if you're just doing it for this first time, you might like learning it this way. Or even if you have taken a course, you might, if you want to take a look. Students actually really liked, because climate, of course, is such an important issue of our day. They really appreciated learning about, where am I here? Let's go. Yeah, they really appreciated about learning about climate science just out of curiosity, even if they never become professional climate scientists. Okay, so this is one way to learn Julia. I guess I could also show you a few things if you like, but you have to speak up and ask. But otherwise, I'll go back to my parallel demo. So so my parallel demo is this, which is that we're going to build our own matrix type. Okay, it's got some fancy.
I have a question.
Yes, please. Hi, Estelle. Thank you.
Yeah.
Yes, somebody would speak up.
Hi. Yeah. So the second matrix, there is it not just a simple covariance matrix when you mentioned that the programming language?
Right. It has the format of a covariance matrix. Absolutely true. So this has the simple format of a covariance matrix. That's right. Good observation. And this is, of course, a diagonal matrix. And so separately, each one of these are very well structured matrices, which there are many, many library operations for. And maybe that's what you're thinking, that, oh yeah, people work with covariance matrices all the time, nothing new there. But my point is that if you add these 2 simple matrices, you get a more complicated object that you don't see very much, right? So that And what I'm about to do cannot exploit directly the properties of this being like a covariance matrix and this being a diagonal matrix. So that's a
Oh,
very,
I see.
thank you for that observation, Estelle. That's great. Also breaking the ice. So now other people might chime in and ask questions, maybe, hopefully. So, alrighty. So here I've got my special type, and it's only going to depend on these numbers v. I'm going to make v bigger than n equals 3. I'm going to take a general vector v. And the only thing I need to really create something that is abstractly a matrix is a size. So that'll be the length of v. It'll be an n by n matrix abstractly. And I have to be able to figure out how to get an entry. And so what this basically does, it says that if I'm off the diagonal, I just multiply, like Estelle was saying, it's just like a covariance matrix. And if I'm on the diagonal, I'm going to also add v. Okay, and so here I'll just give you an example. Okay, now let me go ahead actually, and this was the old supercomputing example, but what I really want to do is go back to Julia Hub, and I've got this example now in VS Code. And so this is the same code I had over there. It doesn't have as many of the pretty pictures. In fact, it doesn't, but it is the same code. And but you might, if you were looking closely, you'll see that I'm calling it a demo matrix here, not an SE matrix. But you could see I was just showing you the size and the get index. Okay, and another thing that's kind of fun if you actually start using this, Matt just showed me this yesterday, there's this little button up here in the browser, which actually takes, it literally takes it out of the browser and makes it like an app on my computer, which I thought was really cool. And so here I have this now as an app on my computer. And let me just do one quick check. I think there's one thing I have to do. Okay, yeah, this is my little check to see if everything's going to work. If I get 12, all right, excellent. All right, this was just an extra. Okay, and so I got a Julia REPL up literally by just going, all I did was grab the line. I'm gonna just did like 1 + 1, and I typed, I'll tell you what I did here, Control plus Enter. Okay, and that actually just executed that line, or in fact, I'll do it again. Right, it copies the line down here. I could also just type directly into Julia here. I mean, there are a lot of other ways to run Julia. Oops. There are a lot of other ways to run Julia. I mean, all the time I go like this, for example, and I can run Julia locally on my machine, right? And you could, I'll get a little REPL over here, 5 + 3, and also one can directly run Pluto notebooks locally on your machine. So here's Pluto, and you can click on something, and I don't know what I'm doing over here. So lots and lots of ways. But today, what we're going to do, is I'm going to run this code directly from Julia Hub right here. Okay. So now, this is a little bit easier to read. So I'm going to kind of show you what I was doing. Alrighty. So I built a special matrix A, and what I wanted to point out is if I do dump of A in Julia, what it does is it kind of show you what's really stored. And you could see that only n numbers, in this case 3 numbers are stored, 1, 10, or 100, right? As opposed to the dumping of the matrix A, which stores all 9 of these numbers, all n squared of these numbers. And so what we're doing is we're encoding an n by n matrix, right? When you think of an n by n array, you think of n squared numbers. But if you think of what underlies this, there's only n numbers, there's only n parameters to build this. And so there's sort of a notion in computing, why store something with n squared storage when n will do, okay? And so you can see that Julia is actually treating it internally as n numbers, even though you in your mind might think of it as n squared numbers, right? And so the computer is oh, there's Philip. We're getting an Amazon delivery, so he's my, I gotta share this. My brother-in-law was telling me the other day that he's so proud. He got his Alexa to tell him whenever he gets an Amazon delivery. I said, I've got a system that tells me when I get any delivery, not just Amazon. So, all right, I think the truck's leaving now. Yeah, my system's better than Alexa. It's very, very reliable. Here I wrote, and I'm not going to go through the details. It's short, but I don't, I don't think that's important. What I'm going to tell you is I wrote my own special eigensolver. Again, this is what I wanted to do. I'm a math guy. I wrote my own eigensolver for my matrices that I knew would be much more efficient than the library's solver. And again, if you have something else you're doing, whatever kind of computation you're doing, just fill it in the blanks for what you're doing. But here, let's do it over here just to show you that I'm not faking it. So here, let's do this one by one right now, just to see what's going on. So first of all, I'm going to run this one by one. So I want to do some distributed computing. Okay, and let me add 4 processors so that I actually have them available to me. And so you could see Julia's evaluating. It's going to be loading those 4 processors, and there they are. It's actually going to be numbered 2, 3, 4, and 5. That might seem a little bit strange, but 1 is the master node, right? And 2, 3, 4, and 5 are like the 4 worker nodes. So that's how Julia does it. And I do need a couple of packages, which I'm going to grab. So I'm going to grab the linear algebra package because I'm doing a linear algebra application, and distributed arrays because I'm going to be doing some parallel computing, and I'm going to do some CUDA, which is the NVIDIA language of GPUs, and it's just the name CUDA. From a Julia point of view, you don't even have to know. Like I have students that walk around MIT saying, I'm great because I know CUDA. I know how to program a GPU. And I go back saying, I think what I'm doing is even better because I can get CUDA and I don't even have to know CUDA. I can just write Julia, and that works just fine for me. So that's what's going on here. Here, let's go ahead and actually execute the code that I showed you before. I'm going to have my demo matrix. Wait, what have I done? I didn't highlight the right stuff. Sorry, let's do that again. There we go. Okay, and like I said, I need a size function and I need a get index function. Here is my demo matrix that I showed you before actually running, and you could see that it's only storing 110 and 100. Here's what it would be stored if you convert it into a full matrix. And now there's my special eigensolver, which I'm not going to explain to you, but I'm just going to run it. And all I'm going to do is show you that my thing gives an answer of 10,200, and the built-in library does it slower, but it does it at 10,200 as well. But here's the important part. I'm going to now go ahead and put this onto a GPU. And the only thing I need to do is basically, in effect, change the type. I'm going to turn this into a CUDA array. I don't love that name. I would have preferred GPU array, but.
So I have a question before you move on.
Perfect, Estelle, thank you.
I kind of miss out why basically using the inbuilt matrix stores n squared and you using the A only stores n.
So here, let's talk about that a little bit. And at the same time, I could show you a little bit of basic Julia at the same time. So the question is, what is it that lets me sort of store n rather than n squared entries? And let me see if I could give that same idea. Oh, I've actually have it here. Let me do it this way. Let me go back to my computational thinking class, and I've got a nice example here that I think you'll like. I think it was in here. Was it in here? Let me just see if it was in here. Oh, if it wasn't here, then I don't know. Then I'll have to remember how I did it. No, it wasn't in this one, and I don't have a good search. All right, so let me make up an example. Never mind. I'll just remember how I did it. Okay. So here, here's a little fun exercise for all of you. In machine learning these days, people talk about a one-hot vector, right? So let's just type that. A one-hot vector. That's a concept. That's sort of a term that's used in machine learning a lot these days. A one-hot vector. And what a one-hot vector is basically a vector. I mean, it comes from a world of zeros and ones, bits, where there's basically one element is hot and another element is cold. For example, I'll just give you, here's a one hot vector here, let's call it V. All right, and you see it's a 6-element vector, and the 4th element is hot, right? The 4th element is a 1. All the other elements are 0. Okay, so one could create, we could create a one hot vector in Julia, a function that will actually create one. Let's just do it, and by doing this, you could actually see Julia in action. Let's see, what are the arguments you would need? You would need a you would need a size n and a k, which is who's going to be hot, right? And I guess one way, there are a lot of ways to do this, but I guess what I could do is I could do it with a for loop. Let's do it with a for loop. I mean, there's so many ways to do this. I'm not quite sure how I want to do this, but here, well, you know what I'll do? I'll just create, just to be easy, I'll create a vector of zeros of length n. Okay, and then what I'll do is I'll just, let's do it this way. I'll just go v of k equals 1 end. All right, so this is a one hot vector. Now I can construct the vector that I just did. Did I not do it right? V equals, oh, did I not return? Oh, I didn't return V, silly me. So let's go back. This is why you put it in the editor. But I'll just do it this way. Is it, I can't copy and paste because I have to give it permission. Allow, okay. So let's do it right this time. Return V, end. Okay, and now you'll see I built the same thing. But this thing, the storage of this thing is 6 numbers. Now, if I asked all of you, how many numbers do I really have to store to encode this object? Right? And the answer would be just the 2 numbers. Right? You should be able to just do this with 2 numbers. Okay? And so there ought to be some sort of abstract way to store the 2 numbers, 6 and 3, and be able to somehow convey the same information. And so let's see how you can do this in Julia. Let me see if I'll get it right. And I might ask Matt to keep me honest here. So let's do my one hot vector. This is like a new vector, and n comma k. And I'm going to create a data structure where n will be an int, a k. Oh, let's do one thing actually. Let's make this a subtype of. Is abstract vector a thing in Matt? Is that going to work?
Yes.
All right.
Yep.
Perfect.
You want to do get rid of the parentheses though. You don't want those parentheses.
Oh, I don't want these parentheses. That's right.
Right.
Does this work or not?
No. You gotta
No.
cursor back.
I should have done it in the editor. But anyway, okay, yeah.
And you'll want to do curly braces with an int inside it to define the element type.
Oh, I'm not going
Right
to. How about I not do that?
Yeah, it might work without it.
I think it will.
Happens.
I think it will. So, oh.
Yeah, you do need the curly braces.
Oh, okay.
That's what that error is telling you.
Oh no. All right. All right. So let's do it up here. Let's do it the right way. All right. You've convinced me to. I'll put it at the top though. You've convinced me to have better code practice. Okay. So what I'm doing, struct my one hot vector. Okay. And actually, let's give it a. In Julia, we like to use capital letters, so for types. So let's do that. So where do I need the where do I need the curlies?
Right there. Yeah, curlies with an int inside it.
Yes. Okay. All right. And this will do, right?
Yep.
Okay. All right. Now let's do 2 more things. Well, first let's show you what we just did. It's a little bit too big in a way, but all right, so let's just see if this actually works. I want to create, let's see if this will work. What?
Yeah, you got an error when you tried defining that.
Oh, because it's, I missed the little capital H.
Ah.
Okay. I should have made that a capital. This is what happens when you do things like on live television. Now what's
There
the
you
problem?
go. Now the problem is that you're telling
I haven't
Julia
done
that
the
it's an
type.
abstract vector, but you've not defined how
Yep.
to index into
Right.
it and whatnot.
So what I'm going to do next is I'm going to go base.size of a vector. So there's two things I have to do. I have to give a size, and I'm spelling it my one hot with a small h. This is why it's good to get these things prepared in advance. But I wasn't anticipating this question. Base.size will be the n. Right, so let's get that done. And then the last thing I need is base dot, what's it called, subsref?
Get index.
Get index nowadays. Okay, base dot get index v my one hot vector, and that that will be, let's see, the get index. Oh, and I'll need an integer I. You don't, let's just call it I. And what we're going to do is we're going to say that if I is equal to v dot k, we're going to have it print a 1. Otherwise, we'll have it print a 0, say. Okay, this is also maybe a little fancy, Julia, if you haven't seen it yet, but this is called a ternary if, where you can, if this is true, give me a 1, otherwise give me a 0. Okay.
One last thing, Alan.
Yeah.
For the size, you want that to be a 1 tuple instead of just v dot n. You want to put it inside a tuple.
Do I need a comma?
Yep. Trailing comma and close parentheses.
All right, thanks.
The distinction there for those following along is that this is a one-dimensional array, and there could potentially be multiple dimensions that you're keeping track of the size for, and we just want to tell it that there's only one dimension. It's just a vector.
All right, now let's see what happens. My one hot vector of 6, 3. Is this going to work? Yay!
There it is.
Can't really what could I do to get it to be visible? There it is.
Yeah, there you go.
Transposed it, and you could see the 0, 0, 1, 0, 0. But what let me point out that if I dump this, right? If I dump my one hot vector of 6, 3, only the numbers 6 and 3 are stored. So now let me get back to Estelle's good question, which might have seemed like forever ago. So let me repeat the question. I wanted to point out that there's a lot of times where the data has some special structure that is something you could take advantage of if you know how to do it. And so, for example, the one hot vector being a little simpler than my matrix, I thought was a better example, because you could see clearly that representing this, I mean, 6 numbers is not a big deal on a computer, but if it was 6 billion numbers, which can happen in machine learning, and you only wanted the third number to be a 1, it would be crazy to store all of those zeros, you see. And so what you do is you can, this is what abstraction is all about. You can create this object which looks to the user like it's got all those zeros stored, but in fact, inside the computer, it doesn't. Okay, and so that's the answer to your question. That's what I was doing with those arrays. I stored the n numbers, the n parameters, but I use it as if there's n squared. And so I kind of have my cake and eat it too. I get Julia's really very good at this sort of thing, where you get the benefit of being able to use your extra knowledge, if you know how to use it, and get the benefit of performance and storage, and still have it look like you're just working with sort of the naive object. And so that's kind of a nice feature of Julia. All right, I hope that answers the question, Estelle. And I had a little bit of fun playing with this too. Yeah, let's try to make this a little bit less. Let's see if I can use my real estate a little better. Maybe it'll be a little easier to see everything. So let's go like this. Okay, so I mean, I guess I could make it a little bit smaller. I know that I love when people give demos if they use very large print at the expense of real estate. All right, so where was I? Let me remind you where we were. So, I was putting this matrix on the, did I distribute this yet? I've lost track if I've even gone this far. I think, well, we can do it again. So the eigenvalue, is this still running? What have I done? Eigenmax of A, if I hit Control Enter, nothing's happening. Why is that? Oh, am I just not?
I think your terminal's just too small, Alan. Make that a little bit bigger. It's just showing your last expression. It's
Is this, if I made it one notch, everything one notch smaller, would that be terrible? Maybe it would be better.
That's perfectly readable.
Okay, thank you. I think VS Code wastes too much energy on these tabs and on the bottom bar, if you ask me. So, okay. Where were we? Okay, so this thing gives the same answer. This is when I think Estelle asked the question, but it uses less memory and storage. But now the question is, can I go and put this on a GPU? And you see the answer is here. I call this Q array thing, and bump, I'm on a GPU. Okay, or I could distribute it. Now these were small matrices. It's not that interesting to distribute it. I just want to see that you can do that. But let's do something a lot bigger, like a 4 million by 4 million matrix, right? That's huge. Okay, so let's let n be 4 million, and let me get 4 million numbers. Okay, and I'll create this demo matrix, but of course I'm only storing 4 million, not 4 million squared. And here I'm going to put it on a parallel computer. Okay, this is what always happens to me, and then I do it again and it works. No, it's not going to work. Why is it not going to work? Why is it not going to work? That's not good. It just worked before. So why is that not working? Let's see.
Can you show more of your error there?
It probably wants me. Well, let me take a guess that I didn't execute one line. Oh, did I lose my original code? Oh. But I still have it over here anyway. All right, let's get rid of all this and get my original code back. This is what I get for fiddling with things. Okay. Okay. So let's make sure this got executed. And now let's go back down here. Maybe I'm hoping I just forgot to execute something. Let's see. Otherwise, I'll show you the error, Matt. Nope, I've got to show you the error. Let's see what the error is. Task failed exception?
It's because your distributed arrays aren't defined on your processes, on the processes you've added.
Oh, did I not do this one? But if I
think there's a order dependency there where
I must have failed. I think my conjecture was right. I didn't execute that one line of code.
Maybe.
So let's try that again. It's working now over there. Yep, it's fine. Okay, sorry everybody. I missed that one critical line which loads the packages. But anyway, here you see I've got a 4 million by 4 million distributed array. Okay, it's virtually 4 million by 4 million. It's actually 4 million. And now what's the deal with this one?
Yeah, that's where you were having your trouble.
Oh, but now it worked. I don't know. Okay, it's working. So and now I just put it on a GPU, so the GPU array. And now here's the key. This is sort of the finale of the demonstration. The point is we're using the same code on a CPU, a distributed array, or a GPU, completely the same code. nothing has changed other than that we've loaded the array onto a GPU or a distributed, and let's go ahead and actually execute it. And so I'm going to go ahead, first of all, and execute it on the CPU. This is the code that I wrote. So with Julia, you usually have to run things twice because during the first time it'll compile and you don't really want to count the time for that. Okay, and so this was, it looks like this was, did I do this right? It looks like it was 0.3 seconds on, 0.3 seconds on my CPU. Okay, and here's the eigenvalue, by the way, 40,035, just to be sure we get the right answer. Now let's do it. I had 4 processors, if you remember. And so this is the distributed. Again, the first time, don't take too seriously. It took a long time. So the second time around, it looks like it was 10 milliseconds, okay? That's to be compared with the 30 milliseconds on one processor. So we have 4 processors. You might have thought it would divide by 4. It looks like it divided by what did it divide? Divided by 30. That's pretty impressive. Is that what it did? Let's one more time. Let me see what the number was. I'm going to make a note of the number. Okay, let's see. Yeah, it's 0.30 on my CPU. I don't know how I'm getting such a good time on 4 processors.
I think your dist A is still smaller. It's giving you a different answer.
My dist A is not the right dist A?
Yeah,
oh,
a tiny one.
What? Oh, that's very strange. Okay.
So yeah, that's where I see. So if you do,
if I just
I'm
run,
not sure.
I don't understand that. Did it not overwrite the
Yeah, so something in your interactive editing there ended up, I think.
Well, let's do the GPU. Will that work?
You can do the GPU. The GPU
That's
will
more
work.
fun anyway.
Yeah.
That's more fun anyway. Well, the GPUA is also not the one that I expected it to be. So it's not executing this line.
Or you missed executing it. Yeah, there you go.
I thought I did all these things. All right, there's GPU. Let's just see. The GPU A is, that's the one. Okay, so I should be able to.
Yeah, there you go.
All right, so why can't I go? I should be able to.
No, you can. You just missed that line.
So the very first time you execute on a GPU, it's actually particularly slow. So you can completely ignore this time, but as it sets things up. But the second time is going to be amazingly, amazingly fast. Okay, so this while I'm waiting for that, I want you at least to see the finale. Okay, there we go. Okay, that's great. All right, so let's run this one again. So that's only 5 milliseconds, which is really, really phenomenally fast to be able to do this sort of thing. So I'm just completely, I'm just not going to get to work. Is that really going to happen?
So I think what happened is one of your distributed workers crashed in some way that what you're doing. You could try removing all your workers and adding them again, or I mean, I think I would just close that that Julia session and restart it. Just close that REPL. Yeah, exactly. And start again if you want
to do it again. All right. So if people don't mind, I'd love to see this working. All right. So here, let's get this started again. Okay. So using distributed, get our 4 processors.
While Alan does that, we are at the top of the hour. And so any other questions that folks have, happy to answer them at this point.
This will be the moment of truth. Look, now I've got it.
Yeah, so something in your iterative, like working with it, you ended up like either missing a definition or changing something, I'm not sure.
All right, so yeah, let's just do the proper timing just so people could see it.
Yeah.
So, okay, 30 milliseconds, that's 300 milliseconds on a CPU. In parallel, same code. First time through, it takes a little while. Okay, now it's 118 milliseconds. So somewhere between what, like a factor of 2 or 3 with 4 processors, which is not unusual. It's very hard to get a factor of 4. It usually doesn't happen. Okay, and then of course the GPU, you already saw it, but I'll just do it again just for completeness. So I'll run it twice. And maybe the last thing I was going to say before we really end, and I could stick around for a few questions for a little while, but let's see, where's my my Chrome window? Oh, that disappeared as well. Oh, is it down here? Okay, let's run this again anyway. Yeah, there it is, the 5 milliseconds, which is truly wonderful. All right, last thing I wanted to say, if I could find my, if I could only find my Chrome window, don't know where I put it. Oh, it's right here. How do I get that back?
It's on the bottom right.
The bottom right. The problem is Zoom puts all these stuff that makes it, oh, there it is, okay.
Yeah, we can see it, but you can't. It's particularly cruel.
There lies the problem. I just wanted to sort of close with some of the parallel computing that's going on in my world over at MIT. So lots of people are using Julia nowadays for some big parallel computing problems. In my world, it's more scientific code, but people are also doing it over in the business school and you know, there's lots of enterprises. I just thought I'll mention that the big climate modeling alliance is, you know, between MIT and Caltech is all completely in Julia. The Center for the X-Scale Simulation of Materials is all completely in Julia. Not completely in Julia, but Julia is sort of like the key part of it. You know, here's the Julia lab. This is my research group at MIT. I'm gonna have to change this. This is a little old now. A lot of COVID-19 stuff, which I think we're all tired of COVID-19. I think we'd like to put it behind us. It's not quite there yet, but we're hoping that it'll get there. So I think we'll concentrate on more of the applications that are more recent. But this is, just so much is going on these days for parallel computing in the Julia world. It's pretty exciting. So thank you for participating. Sorry, I probably didn't hit enter in the right place, but that's what happens on live television. It's going to happen to you. It happens to me. So I think none of you are ever surprised when it happens. But you could see the dream of being able to use language to basically have much easier to debug parallel computing codes, which means that you can use it for years to come. You can build it now and have it for a long time. And you could see that Julia Hub is a pretty stable environment for letting you to do that. So thanks everybody. And I'll stick around if there's some questions. Otherwise, go use Julia. Thanks, Estelle.
I have a question.
Sure.
So can I use this GPU with arrays, this CUDA thing locally, right? Or do I need
right hardware for sure?
I see.
Yeah, the challenge is you need an expensive GPU card that can do this sort of GPU compute. Generally, you're talking about like the expensive NVIDIA cards. Those are the ones that are best supported, and they're the ones that use the CUDA ecosystem. There is support for AMD cards as well, but they're not quite as well trod. The NVIDIA ecosystem is a little bit more robust.
That's some of the stuff that we're working on. I don't know if I've got the right slide, but some of it's happening in the Julia lab, some of it's happening outside the Julia lab. But yeah, we're trying to, the AMD one are these rock matrices, as opposed to Q matrix. Again, I hate all these names. I wish it was just maybe NVIDIA matrix and AMD matrix, maybe, or something, or
maybe just matrix someday. That's
just,
the true dream, right?
That is the true dream, that these red letters could just go away. That's right.
Yeah.
I see.
But yeah, you could absolutely
So,
do it if you've got the right hardware on your machine. But a lot of people prefer to just, pay a couple of bucks and just rent it, so to speak. So they don't have to sort of set it up themselves. But that's your choice.
okay. Yeah, so at my institute, we have a lot of V100 GPUs. So I guess I could use, the Q matrix probably there.
Absolutely.
Sounds good. Thanks. Thanks a lot, Rita.
You're welcome. Any other questions? Going once, going twice?
Hello? Can you hear me?
We do.
Hello. So I have a question regarding operations, because you defined the one hot vector, right? And it takes it only takes two numbers to reproduce it. How does that relate to like when you're trying to make operations that like multiplications and things like that? Because I was trying matrix multiplications, then I tried defining my own sort of matrix based on your lectures actually, and then I tried a sort of matrix-free implementation, like a for loop for these operations.
Great idea. Yeah. Good.
And what I found out was that the matrix-free stencil was a lot faster actually. So do you think that it's like a limitation to this kind of vector storage, or did I do something horribly wrong?
So, well, I doubt you did anything wrong, but I mean, maybe a little. Here's my philosophy on all of this. So, firstly, what a lot is built into what exactly an abstract vector or abstract array does, and it is true that the very first thing we wanted the lowest common denominator that would let things work, and so so matrix operations generally do work. Many of them do work, but if you don't create your own methods, or if there are no built-in methods, then you will get the slowest thing that'll probably happen. It'll compute element by element, and it'll just do it, in a terribly slow way. But you see, what's nice is that it works, and what's terrible is that it works slowly. But it's nice it works. But then you, as a user, can then go ahead and add, it's such a combinatorial explosion of things that everybody wants to do. So you personally, you want to have a matrix times vector. You could, and it depends on what notation you want to use. But people usually talk about matrix-free methods as ways of doing matrix times vector by somehow applying some sort of linear transformation of some kind on the data itself. Now, if you want, you could write it in the language with the star, right? You can overload star in Julia with.
Oh, right. Yeah.
Right. And then now, right. So now you have star A, which is, your special matrix with V, which is your special data, whatever special vector, right? And then you could do, your matrix-free function of A comma V, right? And then if you do that, then the language of linear algebra will just work, and of course you'll get the benefit of sort of the speed that you wanted and the functionality that you wanted. You see.
Yeah.
So that would be sort of that's probably what I would do, because I love overloading. I love sort of the notation of math just working. So when you're done, you just go A times V. And I love knowing that secretly behind the hood, something very fast is happening.
Yes, exactly. Yeah, I was just as a quick side note, I was trying bidiagonal matrices, and I thought that defining my own bidiagonal matrix with like -1s and 1s was a lot faster. So that's what I was trying. But I will try.
You might already know that in Julia, bidiagonal is a thing. Is it
really?
Yeah, bidiagonal of, let's say 1, 1, 1, 2, 2.
You may need to using linear algebra first.
I was gonna say, did I do using linear algebra? I didn't remember. Okay, and now let's do that. What?
I think it's
you need to
capital
say
D.
whether it's
I was wondering.
I think it's
No, you have the lowercase d
No?
is right. It's you
Oh,
need to
oh, there's
say
that
whether
upper,
it's an
lower
upper
button.
or a lower.
I always wish they
All
would
right.
just give me a default. How do I do it nowadays? It keeps changing. Is it upper equals true or colon
I
U?
think
It's-
it's a colon U, I think.
Yes, yes.
Yeah, there it is.
Yeah.
It even
Yeah,
looks
that's
pretty,
it.
by the way.
Yes, it
With the
does.
dot. There it is. And a lot of operations will just work. So if you
Right.
if this is your matrix, let's call it B for bidiagonal or something, right? So actually, will B squared work? It won't be bidiagonal anymore. But I think it'll create it creates a sparse matrix. That's cute.
Yeah.
So
it does have something smart there.
yeah. If I did inv of B, that would be just a dense matrix, I guess, or maybe, yep, that's just a dense matrix. It could have been, yeah. So a lot of things just work, but again, if you know more, you can. But the bidiagonal, tridiagonal, symmetric, upper triangular, I think a lot of those things are built into Julia's linear algebra. So you don't even have to do it yourself.
And to be concrete, what that means is that, by default, if you don't implement a special method for it, or if linear algebra doesn't implement a special method for it, then we don't do anything special about those zeros, right? We don't know that there are zeros, and so you have to access those zeros every time in order to do some operation, right? You do the whole matrix. We don't ignore those zeros, but you can, and what linear algebra does is it uses special methods that avoid touching those zero elements and knows that multiplying something by those is going to be not something it needs to worry about. It's always going to be zero.
Yeah, I see. All right, thank you so much for the lecture. Thank you, and for the comments.
Participating. Okay, other last questions? All right.
More questions? Okay, well, thanks everyone for your participation today, and thank you, Alan, for your time and excellent presentation. For the recorded version of this presentation and our past webinars, you can visit the resources tab at juliacomputing.com. For any help with your existing Julia use case or upcoming Julia projects, please reach out to us at sales@juliacomputing.com and we'll be happy to help you out. Thanks everyone and have a great weekend.